Hello friends, it is the lecture number 7. In last lecture we saw the different kind of energies which are involving chemical reaction. Today we are going to discuss here bond enthalpy or it is a bond energy. First of all, you know what is a bond. Bond means it is the force which held the two nuclei with each other. Suppose A is the atom, another is B atom. When AB molecule is formed, it is a diatomic molecule. Here we write, we consider as a bond. But it is not a rigid part. It is just a force which held the two nuclei of A and nuclei of B with each other. So it is an attractive force between the two nuclei is the bond. Basically, when atom A and atom B converts into AB molecule, it is a diatomic molecule, that time bond is formed. So individually A and B has different energies. Okay, so A has own energy, B has own energy, and when they make a bond, that time there is a excess energy which is present in the individual atom is evolved out, energy is released. Okay, so when bond is formed, energy plus, here is the delta H, here is the positive sign, means there is some values here. Positive sign means what? The heat is there. Okay, positive sign, there is no need of sign, but just heat is evolved, released when any bond is formed. And the opposite of this, when suppose we come back from AB molecule to A plus B, there is a individual atoms. So it is the bond formation. Here is a bond dissociation. Okay, so here is the dissociation energy is involved, here is the formation energy is involved. So when bond is formed, energy is released, and when bond is break down, that time excess energy is required. Excess energy is required means there is a absorption of energy, here is a evolution or release the energy. So release and absorption. Okay, so these two phenomena present in when any bond making and bond breaking process. So for bond formation, bond making process, energy is released, and for bond breaking processes, energy is required. Okay, so every different kind of bond has different bond energy. So every bond has different energy because it depends on two atoms. So basically in diatomic molecules like H2, like HCl, like a Br2 means homodiatomic molecule, the bond energy means bond formation and bond dissociation, the energy is always equal to same. How much energy is evolved out, same energy will require to breaking the bond. Okay, so this is the reverse condition. But some polyatomic molecule like CH4 molecule, so here 4 CH bonds are present. When these bonds are present, every CH bond has different type of energy. Because of it depends on one bond is lost, then there is a something happen in nuclei, that's why force of attraction will increase or decrease, that time bond energies are variable and changes. So for polyatomic molecule we consider the average of bond energies, average of bond energy. So if here the total energy will be calculated, then here 4 types of CH bond, so total energy which is divided by 4, the come is we get the average bond energy, and this average bond energy for the CH bond means it is depends on nature of molecule, it is diatomic or polyatomic. Okay, so in your notes I have provided you the list of bonds with their bond energy. So how much energy will require to breaking of bonds, as well as how much energy released when bond is formed. So bond formation and bond dissociation or bond breaking, the energy is always same for the same simple type of bonds. But for polyatomic molecule, for CH, no doubt the bond energy is same. But overall, the total bond energy from CH4 molecule is different. So we take here, we taking here average of all the bonds. But for example, H2 molecule, so here is the HH. So the energy which is released when the HH bond is formed, same energy required to break it, because when we going to individual HH to H2, when we come back, the H2 converts into HH atom. Again, individual atom acquire their own energy. That means same energy required. So here plus energy, and when there is a H2, this side plus energy is required to break it and converts into again HH. So this is a reversible condition. Same energy required here, which is energy release in a bond formation process. So this is about the bond enthalpy and bond energy. The energy which is released when 1 mole of bond is formed, or the energy which is required to break 1 mole of bond. So any 1 molar bond, when they form bonds, that time the energy is released. It is the bond formation energy, and when one bond is going to break it, that time the energy is required. The energy is dissociation energy, and both energies are same. So using this phenomena, we calculate the heat of reaction. We already calculate heat of reaction in last 2-3 lectures. What is the heat of formation or heat of reaction using different kind of formula. But here we can calculate the heat of reaction using same these energies, bond energy or bond enthalpy. So for that, the delta H is the heat of reaction. We simple calculate using the formula summation of bond energies of reactant minus bond energies of product. Summation of bond energies of products. Suppose we consider the examples on based on in next point. Suppose we consider this reaction H2 plus Br2. It converts into twice HBr. So here is the reactant, here is the product. Okay. So here two types of bond. Here a HH bond is present, their own energy which is listed in table. Br means their Br bond, again their energy is listed in given table. So this is the sum of these bond energies of reactant minus here is the HBr bond is present, again HBr bar listed, or it may be given in your given in when problems asked to you, that time it is given. So this energy also available, but we take sum of the product, here we take the sum of reactant. So it is the sum of the bond energies of reactant minus sum of the bond energies of the product. We get the delta H of the reaction, delta H of the reaction. So that time, if this energy is excess as compared to this one, means the energy is evolved out. Okay, so energy is evolved or energy is absorbed is totally depends on what is the bond energy of reactant side and what is the bond energy of product side. Okay, we're going to calculate one by one in our next point. So we're going to start some numerical problem which is based on bond energy. Okay, the first problem which is based on bond energy. What is the problem? Calculate the enthalpy of reaction. The reaction is given here H2 plus Br2 gives twice HBr. So H2 is a gaseous state, Br2 also gas is in a gaseous state when both are reacting same phase. Here is a formation of HBr, again gaseous state. This is a reaction, and what is the given here? The bond energy of HH bond is, it is not a minus sign, is equal to 435 kilojoule per mole. For BrBr it is 192 kilojoule per mole. For HBr it is 364 kilojoule per mole. So bond energies are given. Here we can use two methods to calculate the bond energies, and the two methods are, just a minute. Okay, two methods are used. First of all, we consider first method is, what is the thing is here? When these two, it is a summation. In this process, there is a bond energy release, and here energy is absorbed. Because when there is a HBr, so energy is absorbed, and when there is a H2 plus Br2, energy is released. That means, what happened here? There is H2, Br2, there is energy converts into twice HBr, means here there is a dissociation. There is a dissociation of HH, Br and converts into HBr. So here this is going to be bond breaking. So that means when going to bond breaking, and you know the bond breaking process require the energy, so energy is absorbed. Okay, and there is HBr bond is going to form. That means bond formation happen here. That means here energy is released. So energy is released, energy is absorbed. So here we can calculate. So first calculate energy absorbed. How much energy is absorbed? So in which step energy is absorbed here? So H2 and Br2 is the absorption. That means how much the energy is given for H2? 435 plus there is a next one 192 is equal to 527. 527 kilojoule per mole is the energy absorbed. And secondly, energy evolved. Energy evolved when formation of HBr bond. So here twice into HBr is equal to energy is evolved out. So what is the bond energy is given here? 364. So here 2 into 364 is equal to here 728. 728. Okay. Sorry, it is 627. Here 728 kilojoule per mole. Okay. So when we calculate the energy of reaction, enthalpy of reaction, so here what is the enthalpy of reaction? So it is just energy evolved. How much? 728. And what is the energy which is absorbed is 627. So more energy is evolved as compared to energy which is required. So here totally finally energy is evolved during the reaction, because energy evolved is larger value than energy required or energy absorbed. That means delta H is equal to 728 minus 627. So it is a 101 kilojoule per mole. Okay, so here is a minus sign. That means energy is evolved during the this reaction. Okay, so energy is evolved out, and the answer is minus 101 kilojoule per mole. It is the first method. Second, this is directly method we can use. We already know what is the formula. So delta H is equal to summation of bond energies of reactant minus summation of bond energies of product. Okay, so here the bond reactant side is this one. So here what is the bond energy of H2? There is a 435 plus for HBr there is a 192 minus here is a 2 into 364. So here 627 minus 728. So answer is minus 101 kilojoule per mole is the enthalpy of the reaction using the value of bond energy. It is the first example. We are going to discuss the another example which is based on the bond energies, and we are going to solve it. Okay, the another example on the board or also in your notebook. The second example is given to you. Calculate the bond energy of CH bond. Given heat of combustion of methane, graphite and hydrogen are, the three values are given. respectively, and while heat of sublimation of graphite is 17 and heat of dissociation of H2 is given again 436. Basically, what is the meaning of the given problem? In problem, they are asked to calculate the bond energy of CH bond of methane molecule. Methane molecule itself undergoes combustion reaction. Methyl undergoes combustion reaction. Graphite means carbon. It represented as a carbon because graphite is the allotrope of carbon. And hydrogen molecule going to combustion reaction. That time the combustion energy is given. Heat of combustion is given. For methane it is a 891. For graphite it is a 394. And for hydrogen it is a 286. Okay. Second, the heat of sublimation of graphite is also given. Graphite undergoes combustion first, then it converts into going to be sublimation. So sublimation energy is given. H2 molecule undergoes dissociation. So dissociation energy also given. So there are 5 things are happen. In first thing, there is a combustion reaction. There are 3 combustion reaction. Methane going to combustion, graphite as well as hydrogen. So first 3 reactions are here combustion reaction. So here CH4 molecule. So one carbon, and you know in combustion reaction any carbon compound it converts itself into carbon dioxide. So one carbon required 2 oxygens. So for each carbon required 2 oxygen. Here 4 hydrogens converts into H2O. That means 2 hydrogens required 1 oxygen. Here 4 hydrogens, that means required 2 oxygen. So carbon required 2 and 4 hydrogens required 2. So there are 4 oxygens are required. That's why here taking twice CO2. So it converts into CO2 plus H2O, and the energy, the heat of combustion is minus 891 kilojoule. Second, here is a single carbon, and you already know carbon required 2 oxygen, that's why just O2 molecule is here. So carbon converts into CO2. So it is the graphite. This carbon represents the graphite. Here is a CH4, methane molecule, graphite molecule, graphite. So graphite on combustion, so one carbon converts into carbon dioxide. There is a 1 oxygen molecule is required, and the energy is here minus 394 kilojoule. Secondly, again say hydrogen also goes in combustion reaction. So H2 molecule, so one H2 molecule converts into H2O molecule. So each H2 molecule requires only single oxygen. So we write 1/2 O2, that means single oxygen. We cannot write just O because O2 is diatomic molecule. That's why I write 1/2 O2, that means single oxygen. It converts into H2O. The energy is given. It is the equation number 3rd. So first 3 processes are here. Again, the problem says the sublimation of graphite, the energy is given. So 4th step, it is a sublimation, solid to gaseous conversion. So it is a sublimation reaction. The heat of sublimation is given. So here these 3's are delta HC, this is the delta HES, this is the delta HD. Okay. C means combustion, S means sublimation, D means dissociation. Last one is dissociation. H2 converts into twice H. So there is a dissociation energy, sublimation energy, and combustion energy. The all energies we put here. Okay. And what is the aim of given? Calculate the bond energy of CH4. Means CH bond. So we need to calculate total energy of CH4. But CH4 first of all converts into, the first equation is very important because here the first equation is used because CH4 undergoes combustion reaction. But here what is the product? The carbon present in gaseous state, again hydrogens present in gaseous state. So CH4 at the right side, at the left side, this is the first reaction, the CH4 goes in combustion. Secondly, the carbon in gaseous state is present here. So 4th reaction is important. And the carbon, hydrogen present in single state and monoatomic state, this is, no doubt we multiply it. So these 3 reactions are used here. So to know the overall calculate energy, we operating these 3 equations. Equation number 1, equation number 4, and equation number 5. So operating equation number 4, equation number 5, and equation number 6. Equation number 1, equation number 4, and equation number 5. We operate here. So just write whole equation. So at the right side, there is a CH4, in first equation plus twice O2 plus, okay, so we write the left side of the first equation. In second there is a carbon, it is in gaseous solid state, then H2 in a gaseous state, okay, then write the product of, there is a CO2 plus twice H2O plus this side there is a carbon in a gaseous state plus twice H in a gaseous state. So we write this equation and we say this is the equation number 6. This is the equation number 6 we write here. Okay. So once we write the equation number 6, so first calculate the delta H of the reaction and divided by 4. So first of all we calculate the delta H of the reaction and then we divided this equation by the 4 because here 4 CH bond is present. That means we get the bond energy of single CH bond. Okay, so this is the equation. We already have the value. Means for this, the value is minus 891. For carbon, 2 carbon gas, the value is again there 717. For H22 twice H2, again the value is 436. So we already have the values. But what happened for this one? So we remove or this energy also exists because here in total process the carbon itself undergoes combustion, the H2 also undergoes combustion, so there is no need of these values. So we cancel or we remove out this value from the given equation. We remove out this value from given equation. So now equation 6, so directly we can write equation 6 minus equation second minus, or here equation not a second, there is a equation third minus equation second, or both are same, equation second. So these two equations there is no need of their values, so we subtract or we remove or we cancel their values from the equation number 6. We have already equation number 6 because these three equations mostly operate the CH4 converts into C into twice H. So we going to, there is a sublimation, so sublimation of CH4 directly here gas, so not sublimation, there is a dissociation, or we directly get the carbon in gaseous state or hydrogen is in a single state or monoatomic state. So to this reaction we use three equations because CH4 coming from first equation, carbon gaseous at the product side present in fourth equation, hydrogen present in monoatomic state in a gaseous state present in fifth equation. So we operating these three equations, so we get the new equation is the sixth equation. So equation number 2 and equation number 3 is not useful. That means we cancel out this equation number 2 and equation number 3 from the equation number 6. So we get the another operating equation is equation 6 minus equation 3 minus equation 2. So put all the values of equation 6. So equation 6 means minus 891 plus equation number 4, because here equation, it is a combination of equation 1, 4 and 5. Okay, so this is the value of equation 1 plus equation 4 is 770 plus equation 5 is 436. Okay, minus equation 3. What is the value? Equation 3 has value minus 286, but there are H2 into H2O. Okay, so again we consider here in the given reaction there is a twice H, so two H2 molecules are used. So here 2 into minus 286. So here equation number 3 minus equation number 6 is given and equation number 2 is given. What is the value? Minus 394. I repeat again. We are going to calculate this one. For this calculation we operating three equations. Equation number 1, equation number 4, equation number 5. We write here and we get the another equation. Okay, there are two equations which are not used here. So the equations 2 and equation 3 is subtract from the equation 6. Okay, so here is the equation 6 minus just 2 into equation 3. Why here equation 3 is multiplied by 2? Because of equation 3 says there is a H2. Okay, but here in that side there is a 4H is required, because H2 4H is required. So H2 twice H2 into, it converts into, it's just simple reaction H2 into H2, but here in overall reaction there are 4 hydrogens, means twice H2 is required. That's why it is a multiply by, because this value is only for the H2, but in given reaction there are 4 hydrogens. That's why we consider here 2 into equation number 3 minus equation 4. Okay, so 2 into equation number 3 minus equation number 5. First of all we solve it. Okay, so minus 891 plus this add together plus 717 plus 436. Okay, so this is a minus 2 into minus 286. That means okay, it is a 572 minus minus plus 572. Okay, then this is a plus plus minus minus plus 394. Okay, so you add all together. When you add all together, the answer is minus 891 plus there is a 2250. This is the sum of all. Okay, so is equal to, so this is the minus 891. So overall it larger value we take the sign of this one plus. Okay, and this goes to subtraction. So 2250 minus 891 is equal to 1664 kilojoule. Okay, this is the total energy. This is the delta H. Okay, so this is the delta H. So we have the 4 bonds. So delta H of CH bond is 1664 upon 4 is equal to 416 kilojoule. 416 kilojoule is the energy of the CH bond. Okay, so the remaining problem which is solved in given notes, you can solve, you can try. If there is a problem regarding the remaining problems, any difficulties, you can ask me personally or on the group. Okay, here we are going to discuss one more example. The third example which is given to you, calculate the energy evolved when 39 gram of C6H6, that means benzene, are burned in an open container in a given reaction. The reaction is given to you. It is a C6H6 is the benzene. You all know. There is a 7 by 2 O2 molecules. 7 by 2 O2 molecules means near about 15 oxygens atom gives thrice H2O plus 6 O2, 6 CO2. The energy is liberated or evolved is minus 3264.64 kilojoule. It is the energy evolved during this reaction. Basically 7 by 2, 7 1 half O2 molecules are used. How many carbon? 6. And you know, when carbon is on combustion converts into CO2, so each carbon required 2 oxygen. So 6 carbon required 12 oxygen. Here how many hydrogen? 6 hydrogen. Each oxygen combined with 2 hydrogens, so 6 hydrogens required 3 oxygen. So 3 oxygen, total we need the 15 oxygen. So here 7 1 half O2, that means 15 oxygen. How much? 15 oxygen. Here we consider. Okay, this is the reaction directly given to you. The energy is given here. How to calculate? And what is the calculate? 39 gram benzene evolved how much amount of energy? So this is the energy, the reaction is given. So this reaction shows there is a 1 mole of benzene burn or on combustion produce such amount of energy. So 1 mole of benzene means how many gram? What is the formula of benzene? C6H6. So if we want to know the converts into number of mole, first of all we calculate the molecular weight. Molecular weight is the sum of mass or atomic weight of individual atoms. So here carbon has 12 atomic weight, hydrogen has 1 atomic weight. So 6 into 12, there is a 72 gram carbon in C6H6, and there is a 6 hydrogen, their atomic weight is 1, so there is a 6, so total 78 gram. So molecular weight of benzene is 78 gram, and if this 78 gram is equal to 1 mole, it is a gram molecular weight. It is a gram molecular weight is equal to 1 mole, means 78 gram is equivalent to 1, consider as a 1 mole. So here this reaction is given to you for 1 mole. That means 1 mole benzene means how much gram? 78 gram benzene is equal to how many? Minus 3264.64 kilojoule is the energy. And what is the question to given? For 39. So then 39 gram benzene is equal to, so you can simply, it is just directly one half of this 78, so you directly write 1/2 here, half of this value, or simple the another quantity is given here, then how to calculate? So this goes to multiply here and 70 goes divide here, so it is just cross multiplication. 3264.64 into the 39 goes here upon the 70 comes here, 78. The answer is again same. The answer is 1632.32 kilojoule. Again sign is minus. 1632.32 kilojoule energy evolved when 39 gram of benzene is burned. You can do in calculator this calculation. Okay, so it is about the third problem. The fourth problem also asks same way, so you can calculate. It is for your homework. If you have difficulty, you can ask me anytime. Okay, so put your any difficulties on group. I will solve it. So today we stop here. In next lecture we discuss the another thing. It is the Kirchhoff's equation and all things in the next lecture.